In 6.2, we are now going to use what you did in 6.1 and 6.0, and we're going to use that with triangles. The only issue is that in those other triangles that you were using in 6.1, you knew that the triangles were similar. They gave you a similarity statement. In 6.2, you are going to have to figure out, are these two things similar? And there are three ways you're going to be able to do that. The first way is called angle-angle similarity. This is AA with a little wavy symbol, which means similar. Angle-angle similarity postulate. You do not have to write out that whole thing. You can abbreviate it with AA with this little wave or the similarity symbol. If two angles of a triangle are congruent to two angles of another triangle, then the two triangles are similar. That's what you wrote down. The first way, the most common way, is angle-angle similarity. By the way, if you saw angle-angle-angle similarity, that would also work if there are three angles. But you only need a minimum of two angles in both triangles for it to work. The second way is something called Sas Similarity Theorem. The Sas Similarity is if you have one angle of a triangle is congruent to one angle of another, and the two sides that include that angle are proportional, then the two triangles are similar. So here is where we have to check to see if, while one angle is the same, are the sides proportional. If they are, then you can use Sas Similarity. The third reason is Sss Similarity. That doesn't prove congruency. It proves that they are proportional and or similar. The three sides have to be proportional. They should be fractions that are equal to each other or that reduce to the same amount. And that would make them similar. And why would we want to know this? Because once we know that two triangles are similar, we know that all their corresponding angles are congruent and all their corresponding sides are proportional. In real life, I try to think of examples of how you're going to use this in real life. And the most common places where we use similarity or we use something like this is in recipes. If you ever are going to do some baking over Thanksgiving break, and you're making a set of pumpkin pies, but let's say you have to make multiple pumpkin pies, you usually double the proportions and everything that you're making. Instead of making a whole pie, I want to do half of it. You might half every single item, and that will make the pie taste the way it's supposed to because you're using proportions in real life. The other thing that you might use in real life is becoming less and less prevalent these days is actually photo frames. When I think about this frame that I have of me and my family, there you go. This frame is a certain proportion. This frame is an 8 by 10. And these days, the old days, when you were taking a photo, you would have to crop it or change the proportion of that particular picture so that when you enlarged it or reduced it, it would fit into a picture frame. Your generation doesn't do that very often, very much anymore. You guys just will take any size proportion, cut it, zoom in on a face, chop the face out, and make all these little stamps and stuff. Like it's weird what you guys do. My generation doesn't understand what you guys can do with a cell phone. Let me say it that way. You guys are way more. You don't use photos for frames. Let's say that. Is that fair to say? That you guys use photos for social media, for texting, for Instagram, for snapping and other things, or you don't do it at all. Yes. All right. There's some true people out there. I love it. Okay. So that's how we use proportions in real life. In this worksheet, we're going to see a lot of overlapping triangles. If you see an overlapping triangle, they usually share an angle. This is what it looks like. If you ever see anything there, you have a triangle, and let's say another triangle. This triangle's angle, the small triangle, shares the angle with the big triangle. If they ever overlap, look for a shared angle, an angle that's the same in both. The corresponding angles are also congruent. We can look for AA here. If this was parallel to that, then we would know that this is congruent to that as well, and that could be an AA similarity. The last thing that we wrote down before we get into examples is this example with the right triangles. If you have an altitude to the hypotenuse of a right triangle, if I have an altitude and it's a right triangle, then this makes 3 triangles that are similar to each other. The small one, small, medium, large side is going to be similar to the small, medium, large is going to be similar to the small, medium, large. And I draw these arrows here to just try to make sure that you understand that your hypotenuse, the one across from here, is going to be your longest side. So I usually go short side, middle side, long side of this small triangle is going to be proportional to short side, middle side, long side of the middle triangle, and then the overall large one, short, medium, long side of the big one. They're all going to be in proportion to each other. Literally, it would be something like this. AD is going to compare to DC. Short, medium is going to be equal to CD as it compares to DB, which is going to compare to AC compares to CB. Like, those are the proportions that get set up from the smallest triangle, the middle triangle, and the large triangle. We'll do example 15 together. That's going to highlight what we're talking about here. Anyways, these 3 triangles are similar. The hypotenuse is always the longest side, so keep that in mind when you're setting up your proportions. And I recommend, when you're doing problems like that, keep your proportions lined up by length. It will help everything else out. So now that you have your worksheet in front of you, let's do some examples together. I have chosen number 2, number 9, 12, and 15. 4 examples we can do together. Number 2 says, determine if the triangles are similar. If they're similar, write a statement of similarity. So, here's what we know. When I look at number 2, I know that the vertical angle here is the same as the vertical angle there. Those have to be the same because vertical angles are congruent. The only thing I don't know is I have a side and an angle and a side in this triangle, and I have a side and an angle and a side in this triangle. If they're similar by side angle side similarity, then what's going to happen is the proportions need to be the same. I know the angles are congruent, but are the sides proportional? Is the 9/6 question mark, is that the same thing as the 12/8? That's what I have to check. Longer side over shorter side. Is that equal to longer side over shorter side? I'm using one triangle and the other triangle, and I don't know. How can we check? You can reduce it, or if you want to check by multiplying and seeing if 8 times 9 is 72. Let me actually write that down. 8 times 9 is 72. We do this one. 6 times 12. What is 6 times 12? Are those equal to each other? Then that means that this is the same proportion as that. Are these 2 triangles similar? Yes, they are. by Sas Similarity. So that means PQR, the 6, then we go to the 9, is going to be similar, short to long. It needs to be X, Q, Z. What postular theorem justifies a similarity? We use the side and the angle and a side, and we check to see if it was in proportion on a side angle side. So we use SAS, but don't forget the little similarity symbol. The difference between what we did in chapter 3, where we said triangles were congruent, this is different. This is saying they're in proportion to each other. We got to have that symbol, otherwise it's not full credit. Otherwise that's not correct. Number 9. This is literally how you can use this to do things that you wouldn't be able to do normally. Victoria wants to find the height of a flagpole. Victoria is 5 feet tall. The flagpole's shadow is 70 feet long, and her shadow is 12 feet long. Find the height of the flagpole. Now, literally, this is the kind of math that you can do that most of you would never do. It is something that I have done before. I wanted to know how tall a redwood tree was in my backyard. I was trying to figure that out, and it's kind of hard to climb up a redwood tree. I don't know if you have tried, but it's difficult. So to take a measuring tape all the way to the tip top of a redwood tree, and the very top is very, very, very thin, it'd be somewhat impossible. But we could use this method to figure it out. Let me show you how. Here's a flagpole. Whee, like this. America. Right there. You like that? See? You like America? There you go. Find the height of the flagpole. We don't know how tall it is. We don't know how tall that is. Because climbing to the top of the flagpole is a little bit hard unless you're kind of a monkey. Victoria, though, we got Victoria over here. Yeah, give her some hair. There you go. She's 5 feet tall. Not very tall. The flagpole shadow is 70 feet long. Now, it's easy to measure a shadow because it's on the ground. It's hard to measure the flagpole because it's skinny and it's tall and you have to climb it, and we don't have a ladder sometimes. But the shadow is 70 feet long, and her shadow is 12 feet long. Here's her shadow on the ground. We can measure that. Now, the weird thing about this, and like you may be wondering, like, what the heck is this all about? The sun's over here. It's a beautiful shiny day because there's shadows on the ground. And if you think about the sun being way far away, when you think about the sun's rays hitting this, then the sun's rays are going to hit that same exact angle. If she's straight up and down and the flagpole straight up and down, and we have that same angle, because the angles are the same, these two triangles are similar by angle-angle similarity. Which means if I go her height over her shadow, then I can figure out how tall the flagpole is over its shadow. That's how you could use this in real life. You could figure out how tall the redwood tree is based off of your shadow and the shadow, as long as it's measured at the same time of day. So let's do that. 5 feet over 12. Her height over her shadow's length is equal to the height over the shadow length. Cross multiply. 5 times 70 is going to equal 12 times x. 5 times 70 is 350 equals 12x. Divide by 12. Divided by 12. Comes out as a decimal. 29.16 repeating. Find the height of the flagpole. It doesn't say round, but we're going to round it because if this is in feet and that's in feet, how many feet is? It's about 29 feet tall. It's way easier to measure something on the ground than it is up and down anyway. So this is a nice, easy way to do that. Number 12. It says, explain why the triangles are similar. Then find the value of x. So this is a two-part question. Alright, so I'm trying to make sure I get everything in there. There we go. The first thing that I see, we have the small triangle and we have the bigger triangle. In the small triangle, I'll call it the red triangle. We have an angle at the top that's the same in the red triangle as it is, let's call this the black triangle. The black triangle and the red triangle, they share an angle. It's the same. But they also have that this is parallel to that. Because they're parallel, the corresponding angles are going to be the same. The ones that make the F shape. The ones that make the F shape, because they're parallel, the ones inside that F are going to be the same. Which means these two triangles are similar by the angle similarity postulate. And then it says find the value of x. Now I picked number 12 on purpose because a lot of you will mess up on your proportion, and I want you to see it. If I'm using the red triangle and I do the right side of the red triangle over the bottom of the red triangle, that is perfectly fine. That's not where I see the mistakes. Where I see the mistakes is this. This was right side over the bottom is equal to, what's the right side of the big triangle or the black triangle? It's 16. The mistake that I see is some people are just going to say 10. Don't just say 10. I need the full right side. Or the small one was this. The full right side is 16 over the bottom. I can't tell you how many students just go and say, well, I used the 6, now I'm going to use the 10. You have to make sure it matches in this unit. Otherwise, it doesn't work out. Now that we have that, let's cross multiply. 6 times 2x plus 4 equals 16 times x minus 1, which makes 12x plus 24 equals 16x minus 16. Going to subtract 12x. Going to add 16. I'm going to divide by 4. And get my answer. Last example. Number 15. The below figure contains 3 similar triangles. Round your answer to the nearest tenth. So this is that example that I was trying to show you earlier about the 3 similar triangles. If this is 90, you can just make a little 90-degree angle symbol right there. If that's 90 and this is 56 degrees, then that must mean that this little angle, these two must add to 90. They're complementary. 90 minus 56, I believe, is 34 degrees. So 56 and 34 make 90, plus that other one make 90, which means 34, 90. This other one needs to be 56. And you can kind of see you have angles that are matching up in both of these triangles. And if you look at the big triangle, you have angles that are matching up there, 34 and 56. So all our angles are matching. What they want us to figure out is what is x? What I'm going to recommend you do on this is I'm going to recommend that you make some proportions that deal with small over middle. Here's what I mean by small over middle. If I ignore this triangle and I look at the small and the middle of this triangle right here, just looking at the triangle ABD, the small one is 2. The middle one is x. Small over middle. And I need to compare that to something. So then I'm going to pick the other triangle. My other triangle, small is, I'm looking at this triangle, the smallest one is x, and the middle one is, yep. Now this looks confusing to some of you, but it can be solved. We've done this before in Math 1. So let's just review. Cross multiply. X times x is x squared. You have two x's multiplying each other. This is not 2x, it's x squared. 2 times 8 is 16. What this means is you have something times itself equals 16, and the opposite of squaring something is square rooting something. The square root of x squared is equal to x. Technically, this should equal a positive or a negative, but since we're dealing with geometry, we can ignore the negative value. The square root of 16, I bet you guys know what that is. But we can ignore that negative value, so x is going to have to be 4 in this case. We have found x. The last one that we have to figure out is what y is. Now, I'm looking at this small triangle here where there's a y. I know what x is. There's many ways. We could do another proportion if you wanted to, but since it's a right triangle, and you now know that this is 4, 2 and 4, and that's a y, why not use the Pythagorean Theorem? 2 squared plus 4 squared equals y squared. Let's work that out. 4 plus 16 equals y squared. 20 equals y squared. Square root both sides to get rid of that square. And I'm hoping you remember, we learned how to break these things down and put it in radical form. Does it say? Oh, it says round answer to nearest tenth. I could write 2 root 5. 2 root 5 on my calculator, switch it to a decimal, is the same thing as about 4.4721. And I'm going to round that to the nearest tenth. Here's the tenth place. That's 5 or higher, so this is going to round up 4.5. I'm going to stop your notes right there.